We're going to get into some more examples of exponential functions in a minute, but before we do, I wanted to go back and look at interest because there's a relationship between interest rate and compounding intervals that I think is worth exploring because that's like if you were presented with two different accounts, for example, one that compounded continuously at 7.2% or one that compounded annually at 7.5%, how would you know which one to choose? Well, you could do the math. So we could say, oh, this is a pert, right? If it's continuous, that's going to be a pert. This one is compounded annually, so that's going to be a equals p times 1 plus r divided by n to the nt power. And so if we set this up and like compare the two values, let's say for the sake of argument here, p would be 1 and time in years would be 1 because no matter what those values are, if they're the same for both equations, the conclusion we draw will be the same. So we're gonna compare these. We would have a is equal to 1 plus 0.075 divided by 1 to the 1th power. That would just be 1.075. So that's 1.075. On the other hand, we'd have a equals p is 1, so e to the 0.072 times 1 power. That is 1.07. I had a calculator do this earlier, so I know it's 1.0746. Now notice this one here is higher. So if given this option, we would go to 7.5%. The relationship between these things is pretty fascinating. Like generally speaking, if you can get a better interest rate, you should get it. That's usually going to control. But sometimes, if we're really close, if we're within like 1/10 of a percent, and you're given the option to compound continuously versus compound annually, it's better to compound. It's better to compound continuously, obviously. Um, but if you're ever in a situation where you choose between two interest rates and one of them's like a 0.5% more, always go with that 0.5% more. There's also one thing worth mentioning here. It's called effective yield. It's a way that we can kind of normalize interest rate. Like what would be the effective interest rate we'd have over the course of 1 year? And the way you would do that is set it up real simple. You would say something along the lines of what would be, so if I just had this, which effectively is compounds annually for 1 year, right? That's the most basic representation of interest. Then I could say p times 1 plus r, and I'm going to set it, I'm going to use the same thing here. I'm going to set t equal to 1 also. So I got p divided by 1 plus r over n to the to the n power. Divide both sides by p, we get 1 plus r equals 1 plus r over n to the nth power. And then subtract 1 both sides, we get r equals 1 plus r over n to the n. That is r is like r sub e for r effective. And so, oh, sorry, minus 1. And what that does is gives us like a value that we can then compare. So if you do the same basic thing for this equation, you set this equal to this, and divide both sides by p and subtract 1 both sides, you'd have the same relationship there, and that effective yield can be compared, and you can determine which account would be better that way too. Uh, E comes up a lot, right? There's a whole bunch of applications for E in the real world. It turns out that it's the constant that models continuous growth or natural growth. So what happens in interest? We've just seen that. It happens when we have natural growth of like a population. Bacteria is a great example. So example that in a minute. It also happens with decay, and these are real world applications. It's like really what happens. We can prove that through testing. It's fascinating. It really is the Illuminati of math. I mean that, and like if you are familiar with the what's this thing called? I can't remember right now. Pascal's triangle. That's also Illuminati status right there. In fact, they're very closely related. It's interesting. Um, okay, so let's look at an example of decay. Oh, sorry, not decay, growth. If we have a culture with 1,500 bacteria and they grow at a continuous rate of 30% per hour, how many bacteria will we have after 30 hours? Okay, easy. So this is going to be like we're going to have some quantity, and it's going to be the initial quantity, Q naught, that zero there, that subscript of 0 represents time 0, so the initial amount, times e to the kt power, okay? Where k or RT power, right? R is the growth rate here. And so if we want to figure this out, so Q would be 15,000 times E to the 0.3 because 30% is 23 times 3. Okay, so we do this math here. It turns out that we will have here 36,894 bacteria. And that's rounded to the nearest whole number of bacteria there, okay? It's obviously it would be a decimal, but you just round because you can't have part of a bacteria. So that is how you would do that kind of math. Let's look at a similar problem where we're trying to solve for a different variable, though. Okay, if now I've generalized this because this kind of population growth, when you're talking about this, it applies to anything. It doesn't have to be bacteria; it could be anything. So if there are 5,000 things present in a place after 20 years, and the thing is known to grow at a continuous rate of 5% every year, how many things were there initially? Okay, well, something important to note here is that these units have to match. If they don't match, you have to adjust it. For example, if you knew something grew at a rate of 5% every minute, and you were asked how much would there be after 20 years, you would have to figure out how many minutes are there in 20 years. So the answer to that, of course, is there are 525,600 times 20 minutes in 20 years. So how do we do a problem like this? Well, we use the same equation. Q is equal to Q naught, which is Q naught is initial quantity, times E to the RT. Okay, and if it's population, for example, we would just use the letter P here, and P naught instead of Q and Q naught. It doesn't matter what the letter is. So let's figure this out. In fact, we're trying to solve here for Q naught. We already have Q, so we could say that Q naught would be equal to Q divided by E to the RT, and then we just plug numbers in. So we've started with 5,000 things, and we're dividing that by E to the 0.05, which is the interest rate, or the growth rate there, and we did that for 20 years. Okay, so if we do this math here, I actually haven't done this math yet, so let me figure this out. It would be, oh, actually, look, 20 times uh, 0.05 is just 1. And so we ask ourselves, what is e to the first power? So e to the first power is just e, right? So this is going to be just 5,000 divided by e. And let me do a calculator real quick. 5,000 divided by e. That would be, there was 1,839 things to start with there. Okay, so we can solve for other variables if we need to. It's not a big deal. Okay, switching gears, let's talk a little bit about decay, exponential decay. And we've said before, like this is an exponential function, and if b is less than 1 but greater than 0, then we're going to end up with decay because we'd be raising a number like a number less than 1, for example, 1/2. If I raise 1/2 to the x power, the higher x gets, the lower the value of this gets. Like if the higher x gets, the lower y gets. And so this is how we would think about exponential decay. If the base is a positive number less than 1, then we would have decay. So let's look at probably the most famous, the most useful, or used anyway, example of decay, application of that. Okay, half-life. So half-life actually is like it's a measure of how long it takes for something to decay by half. And for example, if something decays by half in a day, that means that the amount we would have after 1 day would be the initial amount times a half. And if we then said let it sit there for 3 days, well then we'd be three. We'd have a 3, so it'd be 1/2 to the third, or 1/8. So we'd have 1/8 of the thing remaining after 3 days if it decays by half every day. But obviously, it's not common for something to decay by half in a day. It's common to decay by half in some other amount of time, and that amount of time is known as the half-life of a substance. So for example, there are like radioactive elements, like carbon-14. We use carbon-14's half-life to do radioactive dating to figure out how old stuff is, um, and it's pretty cool. So this is the equation for half-life. There's another equation for half-life. I'll show you in a minute. But if we have this equation, let's do an example where we're trying to figure out how long it takes something to decay by half. Okay. Gribladium has a half-life of 561 years. If you start with 100 grams, how much will be left after 100 years? Okay, so we said that Q, the final amount, is equal to the initial amount, Q naught, times 1/2 to the power of how long we let it sit for divided by its actual half-life. So if we plug this in, right, there was 100 grams to start with, times 1/2 to the power of 100 divided by 561. Okay, so now something really important to note here, and it can be confusing, is that only the 1/2 is being raised to the power here. It's not the 100. The 100, if we think about PEMDAS, right, the exponent is before the multiplication. So this whole thing happens first, and then after that we multiply by the 100. And so when you do that, you get 88.38 grams of. That's how much of this wonderful, incredible element you would have left after 100 years. Okay. Going back and looking at decay in another way, right? We said if the base was a positive number less than 1, we'd have decay. But we know how transformations of functions work, right? If I said what is f of negative x, well, that is a horizontal horizontal reflection. It reflects things horizontally. So I would have something instead of this. I would have something that looks like this. Okay, and so that looks like if I was like saying, all right, there's time equals 0. Well, this would be a decay. And then if I multiplied, like if I said that there was like a coefficient there of a, if I made a greater, I would have stuff like I'd have a more stretched out version of the same graph, and there I have decay. And so it can be said then that f of x is equal to b to the negative x. If I'm raising something to the negative exponent, that is also going to model decay, right? Because f of negative x is equal to b to the negative x if I do that. All right, I'm multiplying all the inputs by -1. Everything's being flipped horizontally. Okay, so that idea lets us come up with all sorts of different applications for exponential growth or exponential decay actually, and we can even use e for it. So let's look at one example of that. Okay, this is again exponential decay, and it has to do with half-life as well. You've been given by literally the coolest person alive 20 grams of gribladium. The decay constant, lambda, of gribladium is 0.001234. How much gribladium would you have after 100 years? 1,000 years. So we want to know, we can use any letter for this. Let's use m for amount of material. Okay, to use q, that doesn't matter. M times m naught times e, because this is going to be it's a natural decay, so we're going to use e, and it's going to be to the negative lambda t. So since I have a negative exponent here now, I will have decay. So let's plug these numbers in. M, I want to know m after 1,000 years. So the initial amount was 20 grams times e to the negative 0.001234. And that's then times 1,000. Okay, so what is that? I'm not sure. I gotta type that into a calculator here. E to the power of negative 0.001234 times 1,000. Let's me syntax error. Why? Oh, I did delete that. Fix it. 4 times 1,000. That times 20 would give me, there would be 5.82 grams of gribladium remaining after 1,000 years. Okay, so unfortunately that kind of sucks because gribladium is a very valuable substance and we want to have as much as we can. So that tells me that 1,000 would be greater than the half-life of gribladium, and it should be because actually I think we use the same half-life as the previous problem. So yeah, this is pretty interesting how we have this exponential decay. The functions, this is the same thing as a pert, right? The same thing as a pert. It's just that r is negative now, and we can apply this equation to so many things, and there's tons of applications.